So going back for a little review, we got to talk about inverses. So this was back in Unit 4, functions. If you have a set of points, how do we find our inverse? There it is. Switch the y and the x. So the point 3, 1, the inverse of it would be the point 1, 3. Whatever was your x becomes your y. Whatever was your y becomes your x. You just flip-flop them. If we have a graph, how do we find the inverse? Reflect over the line y equals x. Which the line y equals x is just a line that goes through the origin, has a slope of 1, so it's up 1 over 1, up 1 over 1, up 1 over 1. Which is that line that I have already drawn on the graph there. Not on your notes, but in my notes I do. All right, equation. How do we find the inverse of an equation? Not in the y negative. Switch your x and y first. And then what do you do? Solve for y. So with the equation, you switch your x and y just like you would at the point, and then you solve for y. You got to get into y equals. So those were our 3 ways of finding inverses. So then down here below, I want you to use your calculator, draw the graph of y equals 2 to the x. And yes, I want you to make a table of values, copy some of those points down, but for right now, you're drawing the equation, or the graph of y equals 2 to the x. So we got the first part on there, graph y equals 2 to the x. There's our graph of it with all of our little details. Now they want us to graph the inverse. So again, when you have a graph, the inverse of it is a reflection over that line y equals x. This is also known a lot as the line of reflection. That's a phrase that's been showing up a lot more often, especially on that Regents exam. So y equals x, line of reflection. I can't talk anymore. It's kind of tricky to reflect it over that line, so if you have your table of values, which you should have, all you need to do is flip-flop your points. So negative 2, 1/4 on my inverse would be 1/4 negative 2. And then we would have 1/2 negative 1, 1, 0, 2, 1, 4, 2, and 8, 3. So once you flip those, go ahead and plot your inverse if you didn't already do so. Since our original had an asymptote, your inverse does also. Only that also changes and becomes your y-axis. So our asymptote is a vertical asymptote now after we reflect over that line y equals x. So next part, they want us to figure out what is the equation for the inverse. So if I start with my original equation, y equals 2 to the x. As we said, to find the inverse, we're going to flip-flop our x and y. So x equals 2 to the y. And now we got to solve for y. So how do we do that? I can't divide by 2. 2 is a base. It's not a coefficient. This is the problem that started happening. So they would need to take the inverse of an exponential function, and they can't. There was no way to do it yet. So what they created was the logarithm. So this is the way we would write it. Y, because y is the exponent, and that's what we're trying to figure out. We were trying to get y by itself. Equals log. This 2 is a little 2 down below on purpose. It's called a subscript. It needs to be that way. of x. So what happens is log simply means exponent. So this is saying here, what is the exponent on a base of 2 that would get me an answer of x? So the log allows us to figure out what the exponent is that we are looking for. So before we were looking for our y, using log allows us to actually figure out what y is. So down here, understanding this form right here, y represents our exponent, b is our base, x is what we refer to as our answer. That is our log form. It's the same thing as our exponential form. It's just another way of writing it. Like before in our last unit, when we had a 4, we would rewrite it as 2 squared. It's the same thing. I'm just writing it in a different way. The other thing to keep in mind, log, all it means is exponent. Log is exponent. Log equals exponent. So let's first practice going back and forth between log form and exponential form. Let's take a look at the top of the next page. So we are starting in exponential form, and I'm going to rewrite this into our log form. So here I have a base of 2, an exponent of x equals a 5. So I would rewrite this using the word log, and my base always becomes that little subscript with it. So I had a base of 2. My answer would come next, and it always equals your exponent because log is your exponent. So log has to equal your exponent. Second one, putting that one into log form. Our base is a 4 because that's what has the exponent attached to it. 6 is our answer, and it equals your exponent. Log always equals your exponent. So for that third one, what's our base? 3. So we would put log base 3. Then what comes next? A equals 5. Always equals your exponent. The base is always down there with log. Then your answer then equals your exponent. So now going the other way, it's in log form. I need to rewrite it as my exponential form. So looking at number 4, my base is a 5 because that's the little number down there by log. So that's my base. Remember, it always equals the exponent. So my exponent is x, so it's 5 to the x. And then it's going to equal 125. Number 5, what's our base? 27. Exponent? Thirds. And we're going to equal x. So 27 to the 2/3 equals x. 6, what's our base? 3. Exponent is x. And it equals a. And then our last one there, 7, what's our base? This is what's known as our common log. They don't have a base written because our number system that we use is a base 10. So it's assuming base 10 number system. So if there is no number written, that means your base is a 10. So that would be 10 squared equals w. Moving on to evaluating log. So again, you have to remember, log is simply your exponent. So when you're evaluating logs, what you're trying to do is you're trying to think to yourself, what is the exponent that gives me that answer? So for this first one, what is the exponent on a 2 that gives us an 8? 3. So log base 2 of 8 simplifies to 3 because the exponent on 2 to give you 8 is 3. What about for 4? What's the exponent on 4 to give you 16? 2. What's the exponent on 4 to give you 16? What's the exponent on 3 to get you 1/3? Again, what's our base when there's nothing written? 10. So exponent on 10 to get you 100. Now ln, we're going to talk about that next week, so we can cross that one out for now. How about this one? Exponent on 2 to get you 5. We're going to learn that one also next time. There are going to be some that don't easily simplify down, like that last one. So you may see that. We will learn it, though, in the coming days. All right, let's take a look at our graphing. So our calculator does have a log button if you have not already found it. Where is it? On the left, next to the 7. Is there a base written next to it? No. So then what base is it? 10. Calculator can only do base 10. So if you need to graph with a base of 3, calculator can't help you with that. It can only graph base 10. So we can rewrite this. If I go from my log form, I put it into my exponential form, I have 3 to the y equals x. What is the inverse of that? 3 to the x equals y. I can type that in, and then what could we just do with our table? Flip it. So we can put 3 to the x in there. We just got to flip our table once we get our values. So go ahead, type that in. 3 to the x, type that in under your y equals. So let's see here. If we start with x of a negative 2, you should have 0.1 repeating, which is 1/9. Again, we just have to flip it because we actually want the inverse of it. So negative 1 and 1/3. What's our next point? Because it's 0, 1 in your calculator, so you want 1, 0. Next one. 3, 1. And 9, 2. Those are the ones we should be able to get on there. So go ahead, plot your points. Again, this graph will have a vertical asymptote. So this is one of our parent functions for our logarithmic functions. And I say one of them because as you change the base, they each have their own parent function. But whenever it's just a number with x, that's your parent function. So all of them are going to look like this. Again, you can move these left, right, up, down. You can reflect them just like we do all of our other functions. But looking at our graph over there, what would our domain be? X is greater than 0. Because your asymptote is at 0, so it can't be 0. And it's to the right of it, which would be greater than. Our range. Y is an element of the reals. It could be anything. It keeps going up over there on the right side of it. Keeps going down as it gets closer to 0. Our x-intercept is the point 1, 0. And it has that vertical asymptote at x equals 0. So every parent function for our logarithmic functions are always going to have those same characteristics. Domain is greater than 0. Range is everything. Y-intercept and vertical asymptote. So if we take a look at the next page, that top box just summarizes what we just went through, the same characteristics that they have. So this is going to help you review Unit 4 a little bit here. Transformation rules are all the same. So if I subtract 6 there from x, which ways is going to make my graph move? Right. 6. that's going to make my graph move to the right 6. Now our original one, we just figured this one out. Domain was x is greater than 0. Range was y is an element of the reals. X-intercept at 1, 0. Vertical asymptote at x equals 0. That was our graph we just drew. So if I now take that and I move it 6 units to the right, is my domain going to change? Yes. It would move over also 6 to the right. So my domain would be x is greater than 6. Would my range change? No. Would my x-intercept change? Yep, it was at 1, 0. I'm moving it over 6 units to the right, so where's it going to be now? 7, 0. And our vertical asymptote would also move, and that would be at x equals 6. So a right-left shift for these functions are going to change your domain, your x-intercepts, and it's going to change your vertical asymptotes. Number 2, what's our transformation that's happening here if my negative sign is right there with the x reflected over the y-axis? So if I take my graph and I reflect it over the y-axis, here's a little quick picture of it. What would our domain be for that? If I take it and I reflect it over my y and it's going this way now, what would our domain be? That would make it become less than 0. If I reflect it over there. Would our range change? Nope, still going to be everything. Our x-intercept would be where? It would just be at negative 1, 0. Because I just reflected that over, so it went from positive 1, reflects over and becomes negative 1. Would our asymptote change? No, that would still be at 0. So if you reflect that, it does change your domain again, and it does change your x-intercept. And then our last example on this page, what's happening to that graph from f of x to g of x? It's going up to so considering the g of x function, the one that got moved up 2, we'll say here's f of x. G of x would be there up to. Would our domain end up changing if I just move it up? No. Domain would still be greater than 0. Vertical asymptote would also still be at 0. Would the range change? No. X-intercept? Yes, that would change. It would be kind of hard to find on the calculator. There is a way of doing it. Easier way, x-intercept is when your y is a 0. So if I set my equation equal to 0, we can actually solve this. You would want to start by getting the log by itself. So subtract your 2 over. So negative 2 equals log base 7 of x. And then again, we were just practicing it. What's the other way we could write this? Seven to the negative 2 equals x, put in our exponential form. So then 7 to the negative 2 is 1 over 49. So that's where your x-intercept is going to be. So 1 over 49 comma 0. Last page of notes. No, we're not going to do all these problems. I'm going to pick a few that we're going to work on. So solving log problems. So if you have a log problem and you can't evaluate it like we did before with our log base 2 of 8, we knew it was a 3. Log of 100 was a 2. To solve these, do like we just did. Put it in exponential form. So these problems are in log form. We change it into exponential form, and then we can go ahead and solve them. So taking a look at example number 1, what is our base in example 1? X, yep. What's our exponent? And then it equals 16. So now this goes back to last unit. How do I solve this? The reciprocal powers. It's not always going to be so simple as just a 4. So reciprocal powers is what you want to use for this one. So 4 times 1/4 makes that an x to the first. That's our power to power rule. So then the 4th root of 16 is a 2. This one's a little bit of an easier one. Base is an 81. What's our exponent? 1/2. I'm going to equal x. 81 to the 1/2 means it's the square root of 81, which is 9. So x equals 9 for that one. Let's go to number 6. Number 6, base is 125. Our exponent is an x. It's going to equal 25. This is ones where we have to do the change of base. We have to rewrite the 125 and the 25 so that it's a number to an exponent. What base would we want to use for these? Yeah, 5, sticking out in my head. 5 to what power is 25? 5 to the second is 25. 5 to what power is 125? Third. But this is actually going to be 3x. Why is it actually 3x? Because the x was already there. I have to keep it there. So now what's our rule? Exponents are equal, so I divide by 3. And I get x equals 2/3. Let's try number 7. What's our base for number 7? 32. Exponent is going to equal 1/2. Again, I have to do change of base. So what do I want to use for 32.5? 2. 2 to what power is 32? 5th, so 2 to the 5x, because again, x was already there. 2 to what power is 1/2? -1. So now my exponents are equal. X ends up being -1/5. Ooh, let's go to number 10 next. What's our base on 10? 100. Exponent. And it equals 0.1. 0.1 doesn't help us out too much, so let's rewrite. What's 0.1 as a fraction? 1/10. So then we would want to use tens. 10 squared, and then 10 to the -1. And then our exponents can be equal. So x is -1/2. All right, let's go to 16. What's 16 asking us to do? Plug in 27. So f of 27 equals log base 3 of 27. So again, remember f of 27, that's just a notation thing. Nothing actually happens on that side. This one you can think about in your head. What exponent on 3 gives us 27? 3 to the 3rd is 27. So log base 3 of 27 would simplify to 3. And then 21. Base would be x plus 1. Exponent would be a 3, and then it's going to equal 27. Now what? Raise it to the 1/3. (27 to the 1/3 means it's the cube root of 27, which is 3. Subtract our 1 over, and we get x equals 2.